Over time, still always being made. So what you have to know at the beginning of number 43 is this reaction. NOx and ClO make a stable compound that takes chlorine out of the home wrecking game. In other words, NOx protects ozone because it distracts the chlorine. Michael, what's the question?
Oh, I was just wondering if once one sort of the diatomic one bonds with another diatomic one, like oxygen does oxygen, it's like a pretty stable bond, right? Like
pretty stable, although UVC can split chlorine diatomics, by the way. Some diatomics are more stable than others. I believe the nitrogen diatomic is not breakable by UVC, but I believe that the chlorine diatomic is. I know that the oxygen diatomic is. I believe the fluorine diatomic is not breakable by much of anything. Wait, what is this? What's that? That's right. So it's really sticky, right? That's what you're saying? And so I'm not really sure which ones can be ionized by UVC and which ones can't, but most of them are, first of all, relatively stable compared to many other bonds. And second of all, some of them are so stable that they're even UVC proof. Yeah.
So how is the chlorine into the atmosphere?
You were probably busy excavating yesterday when I talked about how they get there.
No.
Oh yeah, Planck's trap. Whatever. The reason it gets up there is we as humans use chlorine as an active ingredient in a lot of our homemade chemistry. So we've got a bunch of man-made stuff with chlorine. The most common one is this one. So this is the most common reaction, but there's a lot of other ways to get a single in the air.
what does the red underlines on the hot sprinkles?
Those are the ones that are most relevant in this chemistry. The oxygen, as you know, from ozone, the brittle, because those are the ones that most destroy ozone. Okay. So can you cut this back? Okay. That's right, we didn't throw those out. Okay, so I want to talk about this. It turns out that ozone levels in the polar atmosphere are seasonal. As a matter of fact, I will soon explain this curve down at the bottom. Almost all the depletion of ozone happens during the polar spring. Almost all of it. And so to explain that, I'm going to start with my drawing. The spaceship is irrelevant. First, I'm sure you remember that in the polar regions, winter is very much dark and summer is very much sunny. I think we talked about that, right? At the true poles, it's actually 30 days of dark and 30 days of light. But in the entire polar region, the seasons are super exaggerated. Winter is, if not entirely dark, then very, very much dark. And if not entirely sunny, then very, very much sun. There's another thing that I want to remind you of, too. Everything up here you already know, so I'm just going to give you a bunch of reminders. It should all sound familiar. Remember the 0 to 30s, 60 to 30s, and 60 to the pole? Let's talk about the polar cell. Okay? The polar cell starts at a donut. 60 degrees is a ring around the Earth. Do we agree with that? 60 is smaller than 30, which is smaller than the equator, but it goes 0, 30, 60, point. Correct? So all the air which rises from 60 goes up into the higher atmosphere, basically the jet stream altitude, cruises north, and then it all drops on one point. All that wind is concentrated on a really powerful downdraft. And because the Earth is spinning, it looks like a hurricane that's sitting on the North Pole, and another one that's sitting on the South Pole. Those are called polar vortices. Each of them is a polar vortex. I guess so, yeah. I mean, at the true pole, there's a downdraft. So at some times of the year, if you're standing on the North or South Pole, and it's not like a point, I mean, it's like square miles, there's like a downwind that like blows stuff onto your head. It's like a really significant feature of polar exploration, that the vortices are actually really sketchy, because as you walk closer to the poles, that downdraft is pushing snowdrift at you. So, you already knew everything except for the main polar vortex, and you understand that it's high altitude wind dropping, right? Just like it happened in the 30s. Now, we got our polar vortex, we got our winter and summer, and we've got this chemistry that you've already written down, I hope. One last thing that you also know. What are clouds made of? Water. And what happens when you mix water and NOx? You get nitric acid. That's mandatory chemistry. So look, NOx and water in those clouds makes nitric acid, in this case, in snow. This is acid snow. And that polar vortex blows those ice crystals and snow down onto ground. So the vortex plus gravity pulls down NOx in snow. Agreed? Mm-hmm. In winter.
Naturally occurring one.
Naturally occurring or man-made. Whatever. It is a wintertime thing that the polar vortex takes acid crystals and drops them on the poles, which you realize leaves no NOx in the atmosphere when the sun comes out in the spring. Sun comes out, ultraviolet C becomes active and frees up these guys, and there's nothing to distract them. Does that make sense? So without NOx in the air, it fell as snow. The spring sun peels off those free radicals, which ravage ozone. Ozone levels in the poles drop by 1 to 2% each day, because there's nothing to distract the chlorines, and they just eat ozone all day. Hello. Thank you. Oh, hey, thanks for doing that thing last night. How'd it go? Any troubles? Like, what did you do? It's funny, you didn't see me have a thing. No, you don't. Okay. So watch this, because you've got to understand the seasonal pattern. In winter, the clouds and the vortex take out NOx from the air. In spring, the sun comes out and you deplete a lot of ozone. And then, watch this, in summer, you get no clouds because it's sunny all day. So without those high altitude clouds, there's lots of NOx left in the air, so you get this stable compound. And now ozone is safe because the chlorine, if I'm chlorine, I don't want to break you up anymore. I'm in love for good. I've settled down. I'm wearing the ring, yo. So chlorine will combine with the NOx in the summer, and thus you could say that with NOx in the air, chlorine is distracted. So NOx is like a bodyguard for the ozone, and now With sunlight, ozone can recover. You see what I mean about how this is cumulative content? It would be impossible to explain this if you didn't understand the polar cells, if you didn't understand the acid formation, if you didn't understand the chemistry that makes ozone, if you didn't understand the chemistry that breaks ozone. But if you got all that, you can see it here. Please look up. In winter, there's no sunlight, so ozone levels are flat. It's neither made nor lost because there's no UVC because it's winter. Agreed? Then in the spring, with all the NOx having been pulled down as snow, ozone depletion is most rapid. So the spring makes these drop-offs in ozone level. It's very immediate. And then you get a slow recovery in summer and fall because without the clouds, ozone formation happens, but the depletion does not. NOx are distracting the chlorine, so you don't get depletion anymore. In the winter, no sunlight, so nothing changes. And in the spring, you get a big drop-off again. This is our seasonal pattern of ozone. It recovers in the summer and fall, stays flat in the winter, drops quickly in the early spring, recovers in the spring, summer and fall, stays level in the winter, drops off in the spring. I'm done with the ozone unless you have a question.
Yeah, you said it's like 1 to 2% loss a day. Like how long is that? What's the normal loss of ozone for spring?
Well, another way to say this is that the entire ozone hole happens in the spring. So to whatever degree you've lost it in your polar region, southern and northern, that only happens in spring. Ozone, on average, is gained summer and fall, not changed in winter, but whatever amount is lost from the atmosphere, it all happens in the spring. You lose 30 to 40% of ozone levels in any given year. Hopefully you recover all of that, unless humans are adding NOx or adding CFC. Would anyone like to ask me anything about this ozone chemistry? Last call for ozone chemistry?
Yeah, so you said that people want to like put NOx into the air to, is that one of the drawbacks of that?
Well,
Why don't we do that?
I mean, for one thing, it's a lot of NOx. For another thing, you can't keep NOx from reacting with water, right? So you can't tell the NOx, don't make acid, just stop the chlorine. Like, NOx are going to explode. So you have this offsetting impact where, right, I mean, you add NOx for the benefit of ozone recovery, but then that's going to, unfortunately, make more acid deposition and potentially more smog. You know, the funny thing is you've got stable air with ultraviolet and many ingredients, so the Arctic actually has some of the highest smog levels on Earth because it concentrates everything in poles. So the funny thing is in summer, like, this is one thing, but another thing that happens is in summer, you get really gnarly smog up there because it's so much ultraviolet that you get a lot of those reactions.
Can you kind of explain then how the spring peels off the chlorine? I'm
Yes.
I know you explained it probably a lot.
Maybe not. Look, with no sunlight, this doesn't happen. Because you see that arrow? How it says UVC on the arrow? This reaction only happens in the presence of ultraviolet C. What's the source of UVC? In winter, no sunlight, this doesn't happen. In the spring, the sun comes out. So in the spring, you've always had these, but in the spring you add that, so then this will happen, and that's what I mean. the spring sun makes the reaction that makes the free radical. Yes.
But doesn't UVC make the reaction? Why does it also make the reaction for the oxygen?
That's right. That's why ozone levels stay flat during the